Can you see my camera too?
I cannot.
Okay, let me try something really quick.
I see you, but like, or sorry, like I see like your icon, but no video.
Okay, I have to turn off a recording so that my camera gets back on here. Can you see me now?
Yep. Awesome.
All right. Thank you, everyone. I'm really glad to come back and speak at the academia conference again. My name's Yu Wu. I'm a robotics industry manager at MathWorks, the company that makes MATLAB and Simulink. Today, I'm not really here to promote the company products or show you a simulation or something. I'm here to share what I learned from deploying soft robots in a commercial application. So hopefully this presentation will be entertaining for you. And also in the process, you'll see what some of the work you're doing now in your research, in your when you're doing modeling and simulation, how those work extends beyond academia into the commercial domain. So first, just to tell you a little bit about myself, I got my PhD degree from MIT in 2018 with a focus on soft material robot. And right after, I started a company called Watchtower Robotics, where we put tiny robots into underground water pipes to inspect for leaks. And then 2 years into the startup, we failed. We ran out of money. And then I joined MathWorks as their robotics specialist and help promote their products to robotics companies. I'm also a recipient of Forbes 30 under 30 when I was under 30 years old. And I'm also a recipient of the James Dyson Design Award in 2018, which I actually highly recommend all of you here who are doing all this wonderful soft material robot work to look up this Dyson Award and see if you can also be one of the awardees. I'm also a alumni of Techstar, which is the startup community and startup incubator program. If you are thinking about transitioning your technology, your design, your research into a startup, try Techstar. They are a great program to help you learn a lot of the fundamentals of how to do a business. They also provide seed money to help you get started. So today, I want to talk, my story will be in two parts. First part, I want to just tell you what we learned, like the story of me putting a robot, building those little robot in the lab and then taking it into real world applications. So you see here on the right, this is a picture of that leak detection robot I built. It is basically a rubber Bloomington, you would say, and then it flows with water in the pipes, and it has those blue membranes you'll see there. Those are functioning as sensors to pick up leaks. I'm going to reuse one of my very old conceptual video to show you how it works. So you see this tiny robot here, and then those blue membranes are, like we call them the membrane sensors. You could call them flappers as well. And then they stretch, and they can detect all those stretch whenever it's pulled by a leak in the pipe, and it's connected with a flexible support to the rubbery body that has all electronics in it. It's completely wireless, no tethered, and it can bend, so it can go around the pipe bends. When it's flowing in the water and when the pipe is pressurized, whenever this blue membrane go past a leak, there's a suction force will pull on the membrane, and by detecting the deformation of the membrane, we can know if it's a leak or if there's no leak at all. And you will also say a lot of times there are other things in the pipe like dirts, bumps, and those. We have to design ways to detect those bumps so that we know it's a bump, not a leak. All of them put some kind of friction force, drag force on it, but the direction of the deformation is different. So this is the robot, and when we actually going to use it in the field, we put them into the underground water pipes through hydrants. So when in real operation, we'll actually take apart the hydrant, drop the robot into the pipe, then connect the water hose so that it's pushing water through the hydrant, and the robot then moves in the pipe. Once in the pipe, it just flows with the water and performs that detection along its way before it gets to the other end of the pipe, which is another hydrant, and come out. And then we can download all the data from a robot and then put it into called a Google map for leaks. This is a pretty it looks pretty easy on the video, but in reality, there was a lot of work to get the robot in and out of pipes. You probably don't really expect that when you are working in the lab, but once we take it to the real water system, it is pretty hard. So let me go to next slide. Right. So when I was in graduate school, that's the tiny robot I built, and I'm part of the Mechatronics Research Lab group at MIT. This lab has a long history of building robots with rubber material. We were building like robot fish, robot stingrays in the past, and then we found about this very unique application where we can build soft robots for pipeline inspection. Actually, it does some real good for the world. And then after I graduated, we started a company called Watchtower. We build those robots to bigger so that we can have one robot for each size of pipes, and we continuously to improve it. We also went from myself to a team of, here it's a team of 8. That was in 6 months, and then in a year and a half we were at 21 people. And then this was a picture when we bring the whole team to see a real deployment in the city. And we didn't really start out putting robots into city water pipes right away. We started in the countryside. For example, here, this was back in Indiana, US. Some of you may know. It's where there are a lot of cornfields. And then we take a hydrant out and then put robots into it. And once we make sure the robot works in the real water system in the countryside, we take it to the cities and then put those robots into the hydrants you typically see in your community, and then flush it down the street, take it out from a couple of streets after. It was all pretty fun, and we were making real good progress. But as you know, in the business world, it's not just about engineering. There's a lot more to it. We actually ran out of money after 2 years of operation. And today, I want rather than talk about a lot of things that worked and didn't work in a startup. I really want to share what the things I wish I know before I get into the startup space. And very particular to this conference, this workshop, and everyone here who are interested in simulation software, I want to really share how I think about it after reflecting on my failures and how to use Simulink in a robotic startup. So let me first show you one thing. This is a Gantt chart. You probably see a lot when you're planning projects. And this is what we were doing when we had 3 people in the company. We were doing one project after another, and I being the person who, the technical founder who knows most about this technology, I had to train other engineers we hired to do the same. And then I really had to be on the first project, work with everyone hands in hand, and then move on to the next project. It doesn't really scale up. We are doing things very slowly, and my availability drives our speed of innovation. So then you would think, how do you address this? How do you do more faster? Definitely go hire people. What if you hire 3 times more people? And that's what we did. We hired, at one point in time, we had 9 engineers and later 11 engineers reporting to me. And I hope that when I hired them, I hope that by growing the team size, I could start to do things in parallel. As new projects come in, when I'm working on one project, I could have trained some other engineers to carry out the other projects in parallel so that I don't become the bottleneck holding everyone back. But this is very ideal. You would feel that, okay, through training, I can train everyone to do the thing I know, and then this would actually happen. But the reality is, as long as I'm not working on one of the project, all the other projects, I'm not working on that particular project, that project would take forever. It will take longer because everyone is waiting to ask me questions. There's something they don't know or they're puzzled about, they wait to ask me for questions. And essentially, by hiring more people, we didn't become faster, but in fact, we actually become slower. And that's where I realize the person with the most knowledge can become the bottleneck for the whole team. The fact that you own most of the knowledge and you had a team of people who work with you, you thought that you can train them so they can all solve problems with you. But the reality is they will just come to you when they have problems. And I know most people here in this conference, we are all you're all in an advanced degree program, you probably will become the most knowledgeable person in your team if you actually go into a startup. And I hope this doesn't happen to you. And how to prevent this from happening? I want to first, before we talk about how I think it could be solved, I want to first introduce the concept of institutional knowledge. So this is essentially the difference between I know something versus we know something. My personal know-how, everything I know about this robot design, everything you know about your particular project is your own know-how. But when you are in a team, your know-how doesn't really translate to the team's know-how, but a collection of all the knowledge you have becomes institutional knowledge. However, although this is a collection of knowledge, it doesn't mean every single one of you knows what's going on. And that's actually one of the reasons why it's a bottleneck. You can become bottleneck. So for example, here, this was a picture from the paper I wrote about the leak detection robot. We have a membrane, we're going to detect suction force, and the robot is moving in the water. It's really easy to tell everyone how it works here. But what's really difficult for me to teach others or train other engineers to understand or to do is how you actually figure out the location, how you do all the sensor fusion, all the localization you have to do to figure out the XYZ position of where you detect the leaks, how the system actually respond to false alarms, all these bumps on the pipe, and how the water flow, the fact that water flow is turbulent and we move the robot at high speed affects the performance of this whole leak detection robot. Those are the knowledge I know, and I try to explain to people every time we hire someone new. But essentially, this knowledge, like things you learn in 4 years of your PhD program, doesn't really translate to someone else in one day. It takes a lot longer and takes a lot of experience. And that's when I realized we had to build simulations. I have to turn whatever I know into a model and simulation, so that all the other engineers who join our team can use this simulation as a way to access my personal knowledge. In this way, essentially, I'm putting a digital twin of myself next to every single other engineer we hired, and that turns the whole situation around. Rather than everyone, when they have a problem, they come to me for help. Now they are really still solving the problem with me in parallel, and leveraging the simulation as the way I conveyed our institutional knowledge. So I really encourage all of you to think in this way, that the work you're doing now, all the things you learn, you should translate into a simulation. And rather than focus on training other team members to do what you can do, show them your simulation in a way you actually convey your personal knowledge into the institutional knowledge, and so that you can build a very effective engineering team. And also, simulation is not a one-shot thing, which is the thing I did. When I was doing my PhD program, I did a lot of computational fluid dynamics simulation, all the different simulations to figure out how the system would respond to different speed of flow and all this. But then when I get into the startup space, I'm like, okay, I'm done simulation. I will just keep on making things and learning from the all the deployments, what didn't work, and then put those knowledge back into making the next version. I stopped doing simulation when I get into startup, which is completely wrong now looking back. You should really think about simulation as a tool, a carrier that helps you accumulate knowledge. Every single project I run into, and probably you will see as well, that you don't get everything working in the first shot. You will design, you build, you test, and then you deploy into the customer's site or system, and then you see, oh, that didn't work, that worked. And you really need to carry back all this feedback, all those knowledge into your design again, and then do this whole process in this figure 8 loop. This figure 8 loop usually comes from the software development process, but I think it applies equally well in all the hardware development we may do. And simulation should really be the tool that carries all the feedback into your next cycle of design and also help you in the test process. So now it comes to where I really like about MathWorks, about the tools MathWorks produce, like MATLAB and Simulink. We really provide software to help you to turn your knowledge into the institutional knowledge. In MathWorks, we call modeling and simulation as part of the model-based design approach, where you use a model and a simulation system to help carry out your own personal knowledge throughout the design process and also make the whole design modular so that you can continuously add new information, things you learn from the field, things you learn from the experiment, and improve your model. And you use the simulation every time you make design changes. So, for example, yep, I'll be right there. For example, this one is a Mars rover simulation we demonstrated, where you can model the whole vehicle with all the different electromechanical systems in it, and then put into the simulation environment to see how it runs across a field, and then you can monitor all the different current, power, as well as speed, performance, along this trajectory from your robot. This type of simulation really enables a team of engineers more than yourself to do things in parallel and figure out to track different things, different aspects of design you are trying to make improvements on. And furthermore, we also introduced something called the digital thread. It's part of the Simulink system toolbox as well, where you can track, you can implement those digital threads, and where you track all your design requirements. And every time you make a change, or your teammate of yours make a change to one part of your system, you can run your simulation all over again in one button and see how that design change affects the other part of the system. Do your system still meet the design requirements you're trying to achieve? For example, here, if we are trying to track the speed, and then you made a change to the mechanics part of a robot, you realize, wait a second, I can no longer meet our speed requirements. So those tools like this will be a great augmentation to whatever you are doing in your projects. And last but not least, a lot of times we run into people ask questions. As we're graduating, we won't have access to MATLAB through our campus license, and what do we do? We have this MATLAB Simulink for startups, and the price it's actually pretty affordable. At about $1,000 to $3,000 range, you can get access to all these tools that enables you to do model-based design, enables you to scale up your team and carry out your personal knowledge into institutional knowledge with this kind of tool supporting you. And again, I didn't do everything in the startup myself or anything else in my life all by myself. I always get mentors and advisors to help me in the process. And to me, this is almost like you're simulating life. You're not just simulating a robot or any projects you do. You're taking other people's knowledge into to help you understand what you may be running into in a lot of those life decisions, job projects, and others. And I'm offering myself here. Feel free to add me on LinkedIn. And if you're thinking about startups, you're thinking about taking your simulation skill into jobs, into some professional manner, feel free to ask me. And that's the end of my presentation. Thank you.
Cool. Thank you. That was super cool. Do we have time probably for one quick question from the audience, maybe? Does anyone who's live there want to ask a question? All right, I can ask a question. Yeah, so so just going back to this robot that you were, the pipe inspection robot. I mean, this sounds like a very complicated simulation, right? You have to understand turbulent flow and deformable materials and all these things. Did you write that from scratch, or how would you envision? Like, let's say you were just starting the startup now, and how would you simulate it? Is it simulatable out of the box in MATLAB, that kind of thing?
So first of all, it's not simulatable out of anything right now, and it takes a sequence or a series of tools to do that type of simulation. And just like you mentioned, the soft material robot is interacting with the fluid dynamics, and I actually did